Welcome to the video accompanying our paper, Fitness as the Organismal Performance Measure Guiding Adaptive Evolution. Nature is full of striking examples of apparent design and purpose. To explain this aspect of nature, we use Darwin's theory of evolution by natural selection. But nature is so diverse that you might get the impression that anything is possible in evolution. This raises a question. What does evolutionary theory actually predict? Let's approach this question by starting with Darwin himself. In his book On the Origin of Species, Darwin described the long-term effect of natural selection as the accumulation of innumerable slight variations, each good for the original possessor, and in the second edition as the improvement of each creature in relation to its organic and inorganic conditions of life. By improvement, Darwin meant any modification that would be useful to an individual organism in what he called the struggle for existence. And about the struggle for existence he wrote, I use the term in a large and metaphorical sense, including dependence of one being on another and including, which is more important, not only the life of the individual, but success in leaving progeny. Let's try to make these ideas more precise. Suppose traits are consistently selected for if they improve an organism's performance as judged by some measurable success criterion X. We can think of X as success in what Darwin called the struggle for existence. From this postulate, 2 points follow. First, over many generations, there will be a tendency for cumulative change towards X-enhancing traits. Second, as a result of these changes, organisms will become adapted for achieving high X. And because this includes behavioral striving for high X, we could even go so far as to call X the biological purpose of life. These 2 points are not only central to evolutionary biology, but also play quite an important role for our modern scientific worldview. Creationists sometimes point out that a tornado in a junkyard will never accidentally assemble a Boeing 747. They use this as an analogy to claim that the shaping of organisms by evolution is equally unlikely. But they are wrong because, unlike junkyard tornadoes, adaptive evolution is directed and cumulative. In his book, Climbing Mount Improbable, Richard Dawkins described adaptive evolution as a slow climbing process towards outcomes that would otherwise seem unlikely. This metaphor is useful to illustrate that adaptive evolution, like mountain climbing, is a cumulative and directed process. On a similar note, let me read you a quote by the pre-Darwinian theologian William Paley. Let's say you're walking around and you find a watch on the ground. As you examine it, you marvel at the intricately complex interweaving of its parts, a means to an end. Surely you wouldn't think this marvel would have come about by itself. The watch must have a maker. Just as the watch has such complex means to an end, so does nature to a much greater extent. Just look at the complexity of the human eye. Thus, we must conclude that nature has a maker too. Inspired by Paley's story and by Darwin's response to it, Richard Dawkins invented the blind watchmaker metaphor. This metaphor emphasizes that evolution can build structures, like eyes and brains, that surpass the complexity and efficiency of human artifacts. There is no need for a supernatural creator. Natural selection, the blind watchmaker, is enough. But just as the efficiency of the design of a watch can only be evaluated relative to what the watch is built for, so the design of organisms can only be evaluated relative to what natural selection shapes organisms to do, that is, relative to some success criterion X. So what is the success criterion X that guides adaptive evolution? Surprisingly, especially considering how close Darwin seemed to an answer, this question is still not settled today. Here we suggest that we can infer the answer from the mechanism of adaptive evolution, but only if we are willing to let go of some ingrained but misleading ways of thinking. To get started on this path, let's turn to the question, how does adaptive evolution work? The genes in a population, collectively known as a gene pool, are packaged in individual organisms who express them and develop a phenotype, something we can see and measure. Depending on the habitat, individuals with different phenotypes may be more or less successful, as shown here by a line mapping phenotype to success. If successful individuals contribute more gene copies to the next generation, then this mapping acts like a sieve, allowing genes to pass selectively. We could add more details to this picture, but let's focus on these 5 aspects: gene frequency change, phenotypic change, individual performance, strategy performance, and improvement. Gene frequency change refers to the difference between gene pools at different times. Phenotypic change refers to the associated change in phenotypes. Individual performance refers to whatever individuals do that makes them successful. Strategy performance refers to the adaptiveness of a phenotypic strategy. A phenotypic strategy is the genetically encoded set of instructions that specify what phenotype an individual will express in given circumstances. And by improvement, I mean that, as a result of having their phenotypes adjusted by natural selection, individuals perform better than they would without the adjustment. But each individual lives only once, so no individual organism is cumulatively improved over the generations. Instead, what is cumulatively improved is the phenotypic strategy. So far, I have deliberately avoided the word fitness. Where does fitness come into this picture? Well, it depends on whom you ask. People have different ideas about the concept fitness. For example, when hearing the word fitness, a population geneticist may think of a quantity to predict gene frequency change. A quantitative geneticist may think of a quantity to predict phenotypic change. A behavioral ecologist may think of a performance measure for individuals. A more theoretically oriented behavioral ecologist may think of a performance measure for strategies. And a philosopher perhaps may think of natural selection's improvement criterion. They may also, if you put them in the same room, have animated discussions about who is right. But of course, their answers need not be mutually exclusive. Instead, we may have here a situation like in the ancient fable of the blind man and the elephant. In this fable, several blind men jointly investigate an elephant by feeling around with their hands. The first one grabs hold of the trunk and shouts that it's shaped like a snake, and the next one says it's shaped like a wall, and the next one it's shaped like a pillar, and so on. So let us try to put these ideas all together in a statement we call the central theorem of adaptive evolution. Genes that improve the phenotypic strategy, as measured by their carrier's performance, are usually favored by natural selection, thus directing short-term phenotypic change in a way that amounts to cumulative improvement in the long run. This sounds neither complicated nor unorthodox, but it contains subtleties that make all the difference if we want to avoid some long-standing sources of confusion. Before turning to these finer points, let's first clarify the main outline of the argument. In philosophy jargon, an explanandum is something in need of an explanation, and an explanans is something we invoke to provide an explanation. In our present context, the main explanandum is the purposeful appearance of organisms, here represented by a vertebrate eye and a few of the organisms from our title slide. Our proposed theory is centered around a performance measure for individual organisms. This measure should be chosen such that it predicts gene frequency change, which in turn predicts phenotypic change, which, if it meets the relevant improvement criterion, will affirm our performance measure. These ideas then jointly explain our explanandum. So we have a list of theoretical needs that a fitness concept should fulfill to make our theory work. We can compare these needs against the properties of previously proposed fitness concepts. And that's what we've done. We have identified 3 fitness concepts that meet all 5 theoretical needs. I won't go through this list in detail, you can look it up in the paper. Instead, let me focus on the 3 concepts that have earned all 5 check marks. But as an aside, it's worth noting that many concepts on this list are exclusively concerned with gene frequency and phenotypic change. They miss the crucial ideas of performance and improvement. The first item on the list with all 5 check marks is fitness as lifetime reproductive success. This idea has a long history. For example, back in 1938, J.B.S. Haldane wrote that fitness in the Darwinian sense is assessed by the average number of offspring left. For lifetime reproductive success to deserve all 5 check marks, the following statement should be true. Genes that improve the phenotypic strategy, as measured by their carrier's lifetime reproductive success, are usually favored by natural selection, thus directing short-term phenotypic change in a way that amounts to cumulative improvement in the long run. This is our central theorem with lifetime reproductive success as the performance measure. There are some complications that I skim over here, but at least at a first pass, I hope you agree that this statement makes sense. The next item on the shortlist of fitness concepts that had all 5 check marks was Hamilton's inclusive fitness, which I will write IF Hamilton for short. According to Hamilton, inclusive fitness is the personal fitness which an individual actually expresses once it is stripped of all components which can be considered as due to the individual's social environment, then augmented by relatedness-weighted quantities of harm and benefit which the individual causes to the fitnesses of its neighbors. The highlighted part deserves your special attention because it distinguishes IF Hamilton from the otherwise identical folk definition of inclusive fitness, IF folk for short. folk was the final item on the shortlist of fitness concepts that earned all 5 check marks. According to this definition, inclusive fitness is the personal fitness which an individual actually expresses, augmented by relatedness weighted quantities of harm and benefit which the individual causes to the fitnesses of its neighbors. Note that, since no components are being stripped away here, all of a focal individual's own offspring count towards its inclusive fitness. Now let's find out which, if any, of these fitness concepts is empirically adequate. By this I mean which of them identifies a quantity that real organisms appear adapted to maximize. The organisms we consider here are chosen to cover a broad range of ecologies and life outcomes. The bristlecone pine can reach over 5,000 years of age. The male bird of paradise is attractive to females, but also easy to spot for predators. The worker honeypot ant is sterile and serves as a food storage container for its colony. The termite queen can lay 20,000 eggs daily. At least to a first approximation, the bristlecone pine, bird of paradise, and termite queen all seem well adapted to maximize their lifetime reproductive success. But not so the worker honeypot ant, which never reproduces. Similarly, Hamilton's inclusive fitness, which as you may remember excludes offspring produced with help of the social environment, seems adequate for bristlecone pine, bird of paradise, and honeypot ant. But it fails for the termite queen, who is completely dependent on her social environment. If we would exclude from the termite queen's inclusive fitness all offspring produced with help of the social environment, we would have to conclude that, despite her extraordinary productivity, her inclusive fitness is close to zero. By contrast, all of these organisms seem well adapted to maximize the sum of their direct and indirect reproductive success. Accordingly, they all seem well adapted to maximize their folk definition inclusive fitness. It is worth adding that folk is a generalization of the other two fitness concepts. For example, in the absence of social interactions, there is no difference between maximizing one's folk and maximizing one's lifetime reproductive success. We can now update our explanatory scheme by identifying folk as the relevant organismal performance measure. Let us now turn to the sources of confusion that I hinted at earlier. Going back to our verbal theorem, two details deserve special attention. These are the phrase "that improve" and the word "usually." The phrase "genes that improve" uses the active voice. This implies causality. The genes in question must make a difference to success, not just correlate with it. On the one hand, this is common sense. Obviously, a gene that doesn't contribute to success gets us no closer to a well-adapted organism. But ironically, the very idea of a causal effect has been a major stumbling block for mathematically oriented theoreticians. This is because traditional mathematics cannot express the idea of a causal effect. In the words of the computer scientist and statistician Judea Pearl, it is an embarrassing yet inescapable fact that probability theory, the official mathematical language of many empirical sciences, does not permit us to express sentences such as "mud does not cause rain." All we can say is that the two events are mutually correlated or dependent, meaning that if we find one, we can expect to encounter the other. And the same can be said for statements like "the gene" or "the trait" causes fitness to increase. Fortunately, Pearl has taken the trouble to remedy the situation by developing explicit theoretical tools for the study of causation. But before I show you how this works, let me illustrate the confusion that reigns in the absence of these tools. Here we have two organisms. Each alone makes two babies shown as little circles. This is baseline offspring production. Think of yourself as the blue focal individual. Now, if you help the other individual, you cause it to make an extra offspring, the little blue square. But this is at cost C to your own output of one fewer offspring. So your inclusive fitness, here denoted IF Hamilton, is your baseline fitness, 2, minus the cost of helping, plus the indirect fitness benefit of helping, which is R times B, where R is relatedness. So far, so good. Now, since you have a helping gene and interact with the relative might also have this gene and help you in return. This possibility is indicated by the red arrow. So now you have some probability of producing an extra offspring, the little red square. And that's the kind of offspring which Hamilton's definition excludes. Why did Hamilton exclude it? Why isn't red B in the expression for inclusive fitness? Because this ensures that the cost and the benefit of helping are each counted exactly once. And this leads to a condition that predicts selection for helping correctly when helping increases inclusive fitness above the baseline. By contrast, if we include the red B, we run into a problem known as double accounting. Now a new term appears in the expression for inclusive fitness. Here, F is the probability that you will receive help, and FB is the amount of help you can expect to receive on average. This doesn't exclude any offspring, and so conforms to the Folk definition of inclusive fitness. In contrast to I.F. Hamilton, I.F. Folk appears to predict selection incorrectly, because it includes a benefit, the red B, whose cost, the yellow C, is unaccounted for. This is why many theoreticians reject I.F. Folk. But we argue that this alleged problem reflects a failure to distinguish between causation and correlation. Let me explain. As empiricists well know, we can measure a causal effect by doing an experiment. That is, by conducting an intervention and then comparing the outcome with a control that lacks the intervention. The same idea can also be applied theoretically. If we want to quantify a helping gene's causal effect in a situation with mutual helping, we can do so by comparing the situation shown here to an otherwise identical situation where the helping gene is silenced in the focal organism. This intervention leads to the I.F. value marked with a hat symbol, which equals the baseline plus the help received. The gene's causal effect can then be quantified as the difference it makes when it is or is not expressed. If this difference is positive, we recover Hamilton's rule. So the helping gene's causal effect on I.F. does predict selection. There is no need to exclude any offspring a priori. Recall our 5 theoretical needs. Excluding offspring produced with help of the social environment is supposed to solve a problem. It is supposed to make inclusive fitness a valid predictor of gene frequency change. But it causes another problem. It makes I.F. Hamilton untenable as a quantity which individuals become adapted to maximize. A vivid way to show this is through a thought experiment. You may have heard that Haldane reportedly said that he would gladly give up his life to save 2 brothers or 8 cousins. Let's vary this theme a bit and ask, from the perspective of adaptive behavior, should Haldane discriminate between a child produced with or without help of his social environment? Say, if both could be saved at minimal risk to his own life. Hamilton's definition of inclusive fitness suggests that Haldane should save only the second child, because it states that offspring produced with help of the social environment don't count. But this can't be right. The children's prior history is clearly irrelevant to propagating Haldane's genes in the future. How could Hamilton get things so wrong? Well, actually, he didn't get things wrong, because this is simply not the kind of situation for which Hamilton's definition was made. So you may wonder, well, what kind of situation was Hamilton's definition made for? What do we have to assume to make Hamilton's definition deserve its 5 check marks? The short answer is additive causality. By additive causality, we mean the assumption that the total effect of multiple causes is simply the sum of the effects of each individual cause on its own. For example, this means that when someone helps you, then the magnitude of the effect of their help is independent of your phenotype. So this gives you no control over the birth of those of your offspring, here the red square, which Hamilton's definition excludes. If the red square is a constant that arises no matter what you do, then it is irrelevant to the question of what phenotype will maximize your inclusive fitness. This makes excluding the red square unproblematic if causality is indeed additive. But in reality, causality is not additive. For example, a termite queen clearly does have traits that influence how many offspring she can produce with a given amount of help. For example, her oversized ovaries. How can we modify our scheme to take these insights on board? Well, we can clarify that the performance of organisms, as measured by their I.F. Folk, not merely predicts, but instead causally affects gene frequency change and hence phenotypic change. And we can elaborate that a phenotypic modification must causally improve organismal performance to meet the relevant improvement criterion. Let's turn to the second detail in our theorem that I said deserves closer attention, the word usually. This is another bitter pill to swallow for mathematically oriented theoreticians, because mathematics is best equipped to deal with necessary truths. You can't prove something mathematically that isn't always true. But nature is under no obligation to make life easy for theoreticians. Sometimes genes that worsen the phenotypic strategy are selected for. Envisage a rare mutant allele that encodes a clearly maladaptive trait, say a preference for banging one's head against walls. Let's also assume that this allele is present in 100%, as opposed to the normal 50%, of gametes produced by its heterozygous carriers. then this allele will be positively selected even if headbanging greatly reduces lifetime reproductive success, say by inducing a 49% mortality risk. On a naive interpretation, this example suggests we can predict just about anything about phenotypic evolution, but there are good reasons to reject this conclusion. First, it seems exceedingly unlikely that an allele for headbanging behavior would ever arise in reality. Arbitrary novel behaviors almost never crop up by being encoded by a single mutant allele on its own. Second, even if such a mutant allele did crop up, its effect on phenotypic evolution would almost certainly be short-lived. Why? Because selection acting on the majority of the genome, the so-called parliament of genes, would tend to eliminate the maladaptive behavior. So far, so unsurprising. But segregation distortion is not the only mechanism that can generate gene-level selection for maladaptive traits. Envisage a situation where siblings can help each other, but not if the other individual tries to do the same. In other words, helpers can only help non-helpers. This introduces a non-additivity. A focal individual's received benefits depend on its own phenotype. Let's further assume that helping is highly effective. The beneficiary produces 10 extra offspring at a cost to the focal individual of only 2 of its own offspring. So helping should greatly increase the helper's inclusive fitness. Nevertheless, if encoded for by a gene that is always expressed, helping is selected against in this scenario. This outcome has been called Charles-Worth's paradox. It arises because if every sibling with the helping gene expresses it, then the benefits of helping accrue only to those siblings who don't have the gene. And so far as the focal gene is concerned, benefits that only accrue to siblings who lack the focal gene count for nothing. This has been known since the 1970s, but the wrong lesson has been drawn. The wrong lesson is that inclusive fitness theory rests on restrictive genetic assumptions that are not met in this example. The correct lesson, we suggest, is that Charles-Worth's paradox is a case of gene-level selection for a maladaptive organismal trait. Helping does not evolve here because the flow of social benefits is maximally biased towards particular genotypes. We can call this biasing social benefit distortion, analogous to the segregation distortion I mentioned in the previous slide. The important parallel here is that both types of distortion can lead to the evolution of phenotypes that face counter-selection from the rest of the genome. Support for this interpretation comes from individual-based simulations. Here, the dotted line shows the phenotypic prediction based on inclusive fitness maximization, and the colored lines are simulation runs from different starting points. These results show that the outcome of no helping that characterizes Charles-Worth's paradox doesn't arise under realistic genetic architectures that allow gradual cumulative change. These results support the interpretation that Charles-Worth's paradox is a case of gene-level selection for a maladaptive organismal phenotype. Let's update our explanatory scheme once more. We need to include social benefit distortion and segregation distortion as alternative sources of gene frequency change. These then have knock-on effects on phenotypic change that defy evolution's improvement criterion. From an empirical perspective, these latest additions might not appear important. A few rogue genes won't change the overall trend. But these rogue genes teach us a crucial lesson. Gene frequency change, even if driven by selection, is not synonymous with adaptive evolution. If we treat gene frequency change as synonymous with adaptive evolution, then we can't distinguish between adaptive and non-adaptive cases of gene-level selection. To see the problem, imagine taking a mixed bag of cases of adaptive and maladaptive evolution and then trying to find in this mix a tendency for improvement that always holds. Switching cat metaphors, that would be like the proverbial search in a dark room for a black cat that isn't there. I asked my daughter to draw a 5-colored elephant for this slide. The elephant represents fitness, and its 5 colors represent the complementary aspects of fitness we have been talking about. Each aspect has gained attention in a different subfield. Practitioners in each field are like the blind men in the fable, investigating different parts of the elephant. Let's say population genetics, taking a lead role in the investigation, has a firm hold on the elephant's trunk. Based on their efforts, its practitioners become convinced that fitness must, above all else, predict gene frequency change. This preoccupation with gene frequency change derails the overall investigation in 2 ways. First, without careful reasoning about causality, it appears to rule out the correct performance measure. This is the alleged double accounting problem. Second, if we start out believing that gene frequency change is synonymous with adaptive evolution, then we can't distinguish between adaptive and maladaptive cases of gene-level selection. And without that distinction in our conceptual toolbox, the quest for natural selection's improvement criterion is bound to fail. To sum up, we argue that adaptive evolution tends to optimize organismal design with respect to IFOC. Another way to say this is that IFOC encapsulates both the directionality of evolutionary change and the biological purpose of life. Biologists often use words like biological function, adaptive, cost, benefit that are closely linked to the idea that evolution is an optimizing process. So I want to end by pointing out that if you are a user of such words, then you're a stakeholder in the present debate. What is at stake here for you, I suggest, is nothing less than the meaning of your own words. Thanks so much for your interest. If you want to find out more about this topic, please read our paper.